Lesson 1.2. This is our introduction to functions. Last lesson, well, we discussed lines and we discussed slope, equations of lines. At the very end, I mentioned, really, I was just mentioning notation, but I mentioned linear functions. So why are we doing this? Well, in calculus, a big goal is to study rate of change of a function. And we will discuss this more at the very end in module 4. But okay, what is a function? It's a rule, this is one way to say it, that assigns to each x, and I have this in the domain, a unique number of x. Now, below is where I talk about the domain. This is, think about it as the set of inputs or x values. These are possible values of your independent variable, and the range, these are your outputs is one way to think about it. These are y values, and these are possible values of your dependent variable. Your range consists of things of the form f of x, such that x is in your domain. Now, one thing you've probably seen, but it's very important to review, is the vertical line test. The vertical line test, one way to state it is that a graph is a function, and this is the study of this lesson, provided, well, no vertical line hits the graph more than one time. Let us look at the graphs here in A, B, C, and D and determine which are functions using the vertical line test. Well, this one, A, is a no, because, for example, this pink vertical line hits the graph 2 times. D also is no, because, well, that vertical line hits the graph 2 times. B and C are wonderful. These are functions. No matter where you draw a vertical line in B and in C, you hit the graph no more than 1 time. So what have we concluded here with our vertical line test? Well, here you have function. Here we have function. And then here we have no, this is not a function. And this one, not a function, fails the vertical line test. Now, some important remarks, and this takes us back to the last lesson. Ask yourself, are all lines functions? We were talking about that at the very end last time. The answer is, well, almost. As long as you have a non-vertical line, you have a function, because a vertical line certainly fails the vertical line test. But any other line, this would be one with positive slope, or like this, negative slope, or even horizontal line that has 0 slope, these all pass the vertical line test. So that is my first remark. And the second one, we were using this function notation last time. The domain of this function, linear function, is all real numbers, which is minus infinity to infinity. So before I move and talk about domain of other functions, I just want to make sure everyone's on the same page with interval notation, because this is something that is quite important and we use all of the time in math. Here I'm talking about finite intervals, and A and B are numbers with A less than B. And first we start with an open interval. So suppose here's A and here's B. An open interval does not include A and does not include B, and it would be like this. So we can write that this is all A less than X less than B. Now a closed interval, well, I can just copy and paste the same number line. A closed interval, this does include both endpoints, so we will color them in, and then I can also write this. So A is included and B is also included. This is all A less than or equal to X less than or equal to B. We also have half open intervals. So you notice this is open at A and closed at B. Let's illustrate this now. Open at A and closed at B. Or the second one is closed at A, open at B. Well, what is this set. This is open at A and closed at B. So A is not included, but endpoint B is. And here, this endpoint is included, but B is not. So it's important when we write answers in interval notation, which we will do some today, and you can do some in the exercises. Without a doubt, you'll be doing this in calculus. It's important that we understand the differences in these types of intervals. Now, we also have infinite intervals. Note that infinity is not a real number. And so you will never have closed at infinity because that wouldn't make sense. But this is all real numbers, just as we saw above, minus infinity to infinity. And then we have these other 4 types. This says all x bigger than A, right? A is not included because it's open. This one says all x bigger than or equal to A. And similarly, this infinite interval is all x strictly less than A, and this one is all x less than or equal to A. So let's move into talking about domain, and we will be writing our answers in interval notation. Well, here are 4 examples, and we want to find the domain of each function. We have to think about, what does this mean? Well, if you're given a function, like you see here with the formula, the domain will be the largest set of real numbers such that the function formula is defined. What can we not do? Well, we can't take the square root, or really eventh root of a negative number, and then we also can't divide by 0. Now, we will see more functions in future modules that have some other restrictions, but for now, these are the things we should focus on. So here you notice we have a square root, and what we need is underneath the square root to be non-negative. So let's write it in words, and then we can sort of translate to interval notation. Here we need 4 minus x squared to be greater than or equal to 0. What can I do? I can just add x squared to both sides. And I get x squared is less than or equal to 4. If you're not sure how to go from this to interval notation, just draw a number line. So where is this equal? X squared equals 4. This happens at -2 and 2. And then if you want to help yourself figure out when does this hold, you can just test points. So you know it includes this and includes this, because x squared equals 4 is just fine. But now pick something here. 0. Is 0 squared less than or equal to 4? Yeah, sure. And so I would fill in all of this. Well, now pick something out here. Say 3. Is 3 squared less than or equal to 4? No, it's not. And out here is -3 squared less than or equal to 4. That's not true either. So we have our final answer. We have this closed interval from -2 to 2. This is the domain of this function. In letter B, the issue is dividing by 0. So let's write in words. We need x squared minus 4x plus 3 to not be 0. Well, how can we solve something like this? Let's just factor. We have x and x, and then I need the product of the 2 numbers to be +3 and the sum to be -4. So how about -3 and -1? Now let's check. Multiply these 2 numbers, we get +3. And if we add these 2 numbers, we get -4. So this looks great. Well, this says that x cannot be 1 or 3. And the question is, how do we write that in interval notation? We can do another number line. Here's 1, here's 3. So what this would be, we have under here the open interval 1 to 3. We have here 3 to infinity. And then we have minus infinity to 1. And the only thing required is this is not in our domain. This is not in our domain. We want this part, and this part. And now we can write this. We're ready. This would be minus infinity to 1, union 1 to 3, union 3 to infinity. Here's answer for A and answer for B. Now you notice in letter C, we not only have a square root, but we also have it in the denominator. And so let's write what we need. Well, what's under the square root? Normally, I would do this, right? Normally, I would say greater than or equal to 0 just from the square root. But what happens when x minus 3 equals 0? Then we're dividing by 0, and we cannot do this. So what I need here is strictly bigger than 0. And here I could just add 3 to both sides. X bigger than 3. Well, this one, even though it looked more involved, I think is a little less involved than letter B. So this is just 3 to infinity. This open interval is the domain for letter C, h of x. Now the final one, p of t. Okay, is there a square root or an even root? Are we dividing? The answer is no, not in either one of those. And here the domain is all real numbers. In fact, p of t is a polynomial, and all polynomials have domain all real numbers. So here we just write that as minus infinity to infinity. This is all real numbers as our domain. And so these are some wonderful examples practicing domain and interval notation. Now, we are still going to think about domain and interval notation, but we're also going to be evaluating a function. On the other hand, here we're working just from a graph. When we look at a graph, how do you get the domain? Well, you think about sort of squashing the whole graph to the x-axis. Remember, domain is x values. And the way to interpret these arrows is that it keeps going forever. So looking at this, the domain of this function is all real numbers. The domain is minus infinity to infinity. Now, how do we get the range looking at the graph? Well, it's very similar, except we have to remember that range is y values. So you think about squashing the graph to the y-axis and seeing what gets filled out. So if you sort of move all of the graph this way and see what you land on, you note that we will hit 3, and then we will hit all of this, okay? So here we see the range. It's all real numbers less than or equal to y equals 3. Let's write this in interval notation. It's all real numbers less than or equal to y equals 3, which is like this. Now the final part is evaluate the function at -1. This is a great exercise. It's really important to be able to look at graphs of functions and know what you're looking at as you move into calculus. So what is f of -1? Well, -1 is here. Okay, this is an x value. Maybe I will use some highlighter. Here's x equals -1. And we want the y value corresponding to that. Well, here's the point on the graph. And here is the y value. In fact, I can label the point on the graph. The point on the graph is -1, -1. Okay, and so we see f of -1 is -1. This is the end of letter A. Now we move into B. This function does not have domain all real numbers. You see, this is a closed dot, and so it doesn't continue. So this will be also a fun exercise. and a good one for us. We will figure out the domain, we will figure out the range, and we will also evaluate f of -1, just as we did in the last example. Domain. We want to squash the entire graph down to the x-axis and see what gets traced out. So you see we'll get here, here, here. Now, it's up here is the dot, so it is defined at -1. So on the x-axis, we get all of this. The domain is a closed interval. It goes from -3 to +1. This is the domain of my function. What about the range? This one's a little exciting because we are going to have a union of two intervals. You see what happens when I squash this to the y-axis. I get this -2 to 0. It's open here at 0. So let's write this part first. The range, we have -2 to 0, open, and then we have union, and then we have here, this is 1 to 2. That part's closed. So union this, closed interval. This is the range of my function. Now the final part of this problem, we evaluate at -1. And this is where we have to really understand what we're looking at, because you see it's open here and it's closed up here. The function value is where the circle is filled in. So let me, just like I did in the last example, I can write the point on the graph. So here's -1. The point is -1, 1. This point on the graph is -1, 1. And this tells us f of -1 is +1. I like this example. Now, this is the final thing I want to mention in this lesson, which is quite important in calculus, is piecewise defined functions. So what does this even mean? Well, what this says is, depending on the interval, we have different function definition. So for example, this first one, it says if x is less than 0, the graph is y equals, or f of x equals x plus 1, which means if you're standing less than 0, you look up at the function, you see the line, y is x plus 1. But then also it says the following: if you are greater than or equal to 0, less than or equal to 1, the function is square root of x. So if you are on that closed interval, 0 to 1, you look up, the function is square root of x. And then the last part is, if x is bigger than 1, the formula for the function is 2 minus x. And similarly, if you're standing somewhere bigger than 1 and you look up, the function will be 2 minus x, that line. Okay, so we can use this to evaluate the function at 1, 2, 3, 4, 5 different x values. To figure out which formula you use, just as I was saying, you figure out which interval this x value is in. -2 is strictly less than 0, and so the function is -2 plus 1, which is -1. This is my first answer. Okay, next one. 0, well, it's here in this interval. And so my function is the square root of 0, which is 0. Next one, f of a fourth. Well, a fourth is also between 0 and 1, closed, including the endpoints. And so we take the square root of 1/4, which is, let's see, you could take square root of the numerator divided by square root of denominator. This would be 1 over the square root of 4, and square root of 4 is 2. But this is 1/2. F of 1. Well, 1 is also in the closed interval from 0 to 1. This is square root of 1, which is 1. Now finally, 5. 5 is bigger than 1. So f of 5 is 2 minus 5, which is -3. So I hope this has helped in understanding how to evaluate piecewise defined functions, but we have one more. The first is we want to write the domain of g of x in interval notation, and then we will evaluate g at 4 values. The domain of g, well, we can write this part in interval notation. It's open 0 to 6, and then union, this part is closed 9 to infinity. This is the domain of my function g of x. Now let's evaluate. It's very similar to the one above. 2 is in the open interval from 0 to 6. So g of 2 will be 10 over 2 squared, which is 4. And this simplifies. I can divide the numerator and denominator by 2. So I have 5/2. This is g of 2. G of 5, 5 is also in the open interval 0 to 6. And so I have 10 over 5 squared, which is 25. Now here I can divide numerator and denominator by 5, and I get 2 over 5. G of 9, well, 9 is in this interval, so we use the other formula. G of 9 is 9 divided by 9 minus 6. This is 9 over 3, which is 3. So g of 9 is 3. And then the final one is g of 10. And 10 is certainly in the interval from closed 9 to infinity. And so we get 10 divided by 10 minus 6, which is 10 over 4. And this we can also simplify. Divide 10 and 4 both by 2. 5 over 2. Ah, it's the same. G of 2 and G of 10 are the same. That was sort of by chance, but it's interesting. So this is all I want to say at the moment about functions in lesson 1.2. So I recommend you work some exercises before you move on to the next lesson.